Ahead and do an example problem. A refrigerator uses refrigerant R134A as a working fluid and operates on an ideal vapor compression refrigeration cycle between the pressure limits of 0.12 and zero point 0.7 megapascals. The mass flow rate of refrigerant is 0.05 kilograms per second. Show the cycle on a TS diagram with respect to the saturation lines and determine the following three things: the rate of heat removal from the refrigerated space, accompanied by the power input to the compressor, the rate of heat rejection to the environment, and the coefficient of performance. We're going to go ahead and assume that this is an ideal cycle and that, of course, that it operates as a steady flow cycle. I'm going to go ahead and draw the TS diagram. So we'll get temperature on the y-axis and entropy on the x-axis. Go ahead and redraw that. So here we have one constant pressure line. That would be the at 0.12 megapascals. And here we have the second pressure line at 0.7 megapascals. State 1, we enter in as a saturated vapor. Isentropic compression to state 2 is constant pressure heat rejection to state 3. Expansion to state 4. And then constant pressure heat absorption. Now, what we're going to do is go ahead and analyze from each state. And analyze the properties in each state. So if we go ahead at state 1, we know the pressure is 0.12 megapascals, and it's a saturated vapor, right? So that would be a quality of 1. Make sure if you're using the thermodynamic tables that you go to refrigerant R134A, and if you're using E's, that you would make sure you select the working fluid as R134A. You go ahead and you select R134A for a pressure of 0.12 megapascals, and it's a saturated vapor. You can get that the enthalpy would be 236.7 kilojoules per kilogram. And then we'll go ahead and get the entropy as 0.94779 kilojoules per kilogram Kelvin. Then we go to state 2, which is the at the end of an isentropic process. The pressure at state 2 is 0.7 megapascals, and we set the entropy at state 2 equal to the entropy at state 1, and we can get the enthalpy at state 2 of 273.5 kilojoules per kilogram. Then at state 3, we have the pressure of 0.7 megapascals, and we know that it's a saturated liquid. We can get H3 as 88.8 kilojoules per kilogram. And then state 4, if you remember, is an isenthalpic process. So H4 is equal to H3, which is 88.8 kilojoules per kilogram. Now that we have the enthalpy at each of the states, we can go ahead and compute the process energy energy transfer quantities for each process. So we get that the heat absorbed in the condenser is going to be and the heat absorbed in the evaporator is going to be mass flow rate times H1 minus H4. If you plug in your numbers there, you get 7.41 kilowatts. The work into the compressor will be the mass flow rate times H2 minus H1, since process 1 to 2 is through the compressor. That would be 9.23 kilowatts. And then if you do a first law analysis around the whole cycle, right, we get energy in equals energy out because it's a steady flow device. So energy in will be QL and work in. And energy out is QH. So if we go ahead, and then if you add those two components together, you get 16.64 kilowatts. And then, of course, the coefficient of performance for a refrigerator is going to be the heat absorbed from the cold space divided by the work in, and this refrigerator would have a coefficient performance of 4.06.